this third and last video concerning valence bond theory, we'll look at the situation of carbon making two sigma bonds. Now so far, our focus has been on the bonding involving carbon. The conclusions that we make concerning carbon will also apply to other atoms, and we will look at that in other lessons. So the example that we'll use here for carbon making two sigma bonds involves ethine or acetylene. On the left-hand side, we have a ball and stick representation, and we can see there's a linear arrangement. So starting from, let's say, the carbon that's on the left, it's making one sigma bond to a hydrogen and another sigma bond to another carbon. Or if we look at the carbon that's on the right-hand side, again, one sigma bond to a hydrogen and another sigma bond to another carbon. Note the three lines between the carbons. We can view one of those lines as representing the sigma bond. The other two lines will represent pi bonds, as we shall see. The bond angle here is 180 degrees. Now, of course, there's no way that any one of these carbons could be sp3 hybridized, nor could they be sp2 hybridized, as the bond angle is not appropriate. We will find that bond angles of 180 degrees is associated with sp hybridization. And so let us look at how this works. So looking at the boundary surface diagram representation, this again represents carbon in the excited state. Each one of these boundary surface diagrams of atomic orbitals contains one electron. To form two sigma bonds, we need two hybrid orbitals. So the s atomic orbital hybridizes with one of the p orbitals. In this case, I've chosen the 2px, and will form two sp hybrid orbitals. They will adopt an orientation such that the larger lobes are 180 degrees relative to one another. Perpendicular to the linear arrangement of these sp hybrid orbitals would be two unhybridized p orbitals. Of course, these unhybridized p orbitals can be involved in forming pi bonds. Putting this together, we now see the bond line representation of ethine. Again, one of these lines between the carbons represents the sigma bond. The other two lines represents the pi bonds. It doesn't matter which lines you think of as being the pi bonds. Now moving to the boundary surface diagram, the gray boundary surface representations corresponds to the sp hybrid orbitals. Of course, each carbon is going to have two sp hybrid orbitals. One of the sp hybrid orbitals will make a bond with a hydrogen. The other sp hybrid orbital will make a bond with the second carbon. The representation of blue and then green is one of the p orbitals, and again, blue and green, the other p orbital. Of course, they will have a side-by-side overlap with the corresponding p orbitals in the second carbon to once again form the pi bonds. And so we can add some notes here. In the ethine molecule, we have localized carbon-hydrogen sigma bonds and localized carbon-carbon sigma bonds. We also have localized carbon-carbon pi bonds, and in this case, two different sets. The same thing that we said concerning ethene applies to ethine in the sense that any one of these pi bonds only contains a pair of electrons located both above and below the plane. Now I've gone through these examples, or at least this latter example, relatively quickly because I'm interested actually in the main conclusion. One of the things that perhaps you've noticed already is that the number of sigma bonds that a carbon makes is associated with the hybridization. So here's the connection. If we see that carbon's making 4 sigma bonds, we know that that carbon is sp3 hybridized without having to go through the energy level diagrams. In turn, if the carbon is making 3 sigma bonds, the carbon is sp2 hybridized. 2 sigma bonds, sp hybridized. We also know, by knowing the number of sigma bonds and the hybridization, the approximate bond angles. So any carbon that's sp3 hybridized will likely have bond angles close to 109.5, sp2 close to 120 degrees, and sp close to 180 degrees. This conclusion is important in looking at any sort of organic molecule. And as we will see, will extend to looking at the hybridization and the bond angles of other atoms. To test whether or not this has made some sense to you, I'd like you to try an example. So here we have three different representations of molecules. And what I'd like you to do is, based on the number of sigma bonds each carbon is making, assign the hybridization to that carbon atom. I ask you to stop the video while you do this exercise, and to simplify it, rather than write out fully sp3 and sp2 and sp, just write out 3, 2, and 1. Okay, so I hope you stopped the video. Here is the answer concerning the number of carbon atoms that have sp3 hybridization. The way that I answered this, for instance, is when I looked at this carbon on the leftmost side of this molecule, I noticed that it's making one sigma bond to another carbon and then 3 sigma bonds to hydrogens. This carbon must be sp3 hybridized. Or for instance, this carbon right here is making 2 sigma bonds to other carbons and 2 sigma bonds to a hydrogen. Therefore, it must be sp3 hybridized. Remember, when we have these bond line drawings, that if we don't write in the hydrogens, they must be assumed to be there. So every one of these carbons on the leftmost side of ibuprofen molecule is indeed sp3 hybridized. Moving on, these carbons are sp2 hybridized. Now, one of the things that you're going to notice is that a carbon that's involved in a pi bond is either going to be sp2 or sp hybridized. Just to run through a couple of examples, over here in this carbon, we see that it's making one sigma bond to a second carbon, another sigma bond to a second carbon, and one sigma bond to a hydrogen. It's therefore making 3 sigma bonds. It must be sp2 hybridized. Now, I took a shortcut. For all the carbons in this benzene ring, they are all sp2 hybridized, as they are all making 3 sigma bonds. Finally, these carbons up here are making only 2 sigma bonds, and therefore they must be sp hybridized. Hopefully this video has reviewed hybridization for you and has also made the concept a little more friendly and familiar. This concept is foundational to understanding most of the organic chemistry course, and so I hope you'll take some time to make sure that you have mastered it.